Today we're going to be working on Lab 8, which is the Jupiter Lab. This lab consists of 4 separate sections, and we're going to do a quick introduction of each one of these sections before we actually get into each one of them separately. So part A actually has us focusing on Jupiter's Great Red Spot. Now we know what Jupiter's Great Red Spot is. It's just a giant storm, all right? But we're actually going to really take a look at it and see how big it actually is, all right? And this actually ends up being really massive, all right? And we're also going to estimate how fast it's spinning. Now this is a good prediction of how fast its wind speeds are. And so in part B, we're going to take these wind speeds as we calculate in part A, and we're going to pair it to the fastest wind speeds that we observe in cyclones here on Earth. Okay, and so part C then, we actually turn a little bit and go look at the Galilean moons. So you're given a bunch of images taken over several nights, right, of the planet Jupiter and its moons. Your job is to take a look at those pictures and actually find the orbital radius and orbital period of each one of those moons, all right, and then you're going to identify the names of those moons. Right. Now, the last part, part D, you're actually going to be using Kepler's third law and information that you found in part C to find the mass of Jupiter. All right. So we're going to tackle each one of these separately, and remember that this is due before you come into class next week. Okay, so first we're going to do, of course, part A. All right. So the first thing we'll be doing in part A is estimating the semi-major, semi-minor axes of the Great Red Spot. We're going to assume that it's a nice ellipse, and then using those the A and B that you found, we're going to find the circumference. Okay. So how you're going to find the semi-major and semi-minor axes is that you're going to be using Earth. Now, in this particular case, we've actually given you an image that has the actual size of Earth as compared to the Great Red Spot. And obviously, as you can see, you can actually fit more than one Earth within this giant storm. Okay, so how do we find the semi-major axis? Well, let's say the center of this ellipse is right between these two Earths, right? And so we know that the semi-major axis is the axis corresponding to the longest diameter, right? Just in case you need a reminder, here's a little image down here of an ellipse with a semi-major axis corresponding to this radius, which is the half of the longest diameter, and then the semi-minor axis is here, which is half of the shortest diameter. Okay, so the semi-major axis A, we can kind of look here. It's the distance from here to here, for example, right? And that's actually, it's a little bit more than one Earth diameter, right? Obviously, this whole length right here is an Earth diameter. It's a little bit more than that, but it's not quite 1.5 times the Earth's diameter, right? So a good approximation would just say 1.25. Okay, not quite 1.5 Earth diameters, more than one Earth diameter. So we're going to make a good estimation, say 1.25. Right, so I'm actually going to say 1.25, the diameter of the Earth. Right, and of course you have to put this into a number form because you're given the diameter of the Earth right here. So you need to write this in kilometers. We can find the semi-minor axis B as well, and we know from the diagram below is that it's this point to this right here. Now, if you imagine moving this Earth over here, it's actually a little bit larger than one Earth radius, right? Not the diameter, we're actually working with radius now, which of course we know is half the diameter. So it's a little bit more than one Earth radius, but not quite 1.5. So again, a nice estimation would be 1.25 radius of the Earth, right? And of course, as I said before, you can easily get the radius because the radius is just half the Earth diameter, right? And the circumference is easy. You just plug in these values that you have in kilometers. Okay, plug it into this equation, this circumference equation. Right, so take the same major axis A, square it, add it to the same minor axis B, that's squared, divide that quantity by 2, take the square root of that quantity, and then multiply it by 2 pi. Right, so that'll give you a nice large circumference. All right, so now going further in part A, we are talking about the Voyager 1 spacecraft. Now, from January 6th to February 3rd, 1979, the Voyager spacecraft is on approach to Jupiter, all right? And it's going to take every Jupiter day, so every time that Jupiter rotates, the Voyager spacecraft is going to take an image of the Great Red Spot. They're on the same position every image. All right, so in this time period, which is about 28 Earth days, right, the Voyager spacecraft is taking an image every Jupiter day of the Great Red Spot. We'll make that more clear as we go to the questions. But on page 4, it's giving you 12 of these images. 12 of these total 60 images. All right, and these images are special because, as you see, well, first off, you can see that Jupiter looks to be getting closer and closer. Well, obviously, that's because the spacecraft itself is getting closer and closer, so that kind of makes sense. We can see that in this particular image, image 1, we mark a certain place on the Great Red Spot, right? And every image, we also mark the same spot, and we can see that that spot's actually moving around, right? And these 12 images are special because it takes 12 images for the X to get back to the same spot that it was on the first image. All right. And this is going to be important because if we know the image between each picture, then we know the total time it takes between image 1 and image 12. And that tells us the time it takes for this X to get all the way around. All right, and that gives us a velocity if we know the circumference, which we found before. So that's just an overview of what we're going to end up doing. So question 1. Question 1 says the image on the previous page shows 12 images out of 60 total images taken over 28 days. Approximately how many hours on average pass between each of the images being taken? All right, so let's actually get up a whiteboard app. All right, so we want how many hours on average passed. All right, and we have a total amount of time. The total amount of time is 28 days. Well, we need hours, so we need to do 28 days. We know 1 day consists of 24 hours. And so days cancel, we multiply across. 28 times 24 is our answer for how many hours are in 28 days. Well, in those 28 times 24 hours, we take 60 images, and we're going to assume that those images are taken equally spaced apart, which they are. They're separated by 1 Jupiter day. But we want to know how many hours that is. So we take the total amount of hours we have, which is 28 times 24. Total hours divided by the number of images we have. Right? And that equals 28 times 24 in the numerator over the number of images, which is 60 total. Right? So this will give us, this is the number of hours between each image. All right. Now question 2. Now we need uses question 1. And now we want to know how many hours are covered by the full set of 12 images all taken in sequence. Now the 12 images is referring to are the ones above, right? Well, this is easy because now we have the image, the number of hours between each image, right? And we have 12 images, but there's one thing we have to take into account here. I'll show you that in a second. So, if we have a certain number of images, let's say 5 images, all right? We take an image at time equals 0, and then some time passes, we take another image, same amount of time passes again, we take another image, same time passes, another image, and then we take the 5th image, right? This is 1, 2, 3, 4, 5 images. We only have 4 time periods. 1, 2, 3, 4, not 5, right? And so if we knew the time period between each one of these pictures, the total time it takes for the 5 images is actually 4 of these time periods, not 5. And so this actually applies to question 2. How many hours are covered by the full set of 12 images? Well, we know how many hours. So for example, we know this time period for those 12 images, right? But we don't have 12 of those time periods, we have 11, right? And so we want the hours it takes for 12 images. That equals to the hours between each image times the time intervals. Intervals, that's what that says. All right, so the hours it takes for 12 images equals the hours between each image, which we found it was 28 times 24 over 60. And we just discovered that the time intervals, it's not 12, it's actually 11. Right? And that'll give us a nice, solid answer for question 2. Now question 3. Question 3 has us finding the velocity. We'll see why in a second. Question 3, we're going to take the circumference that we found earlier and divide it by the total number of hours covered by the 12 images. All right, now this is getting into the velocity like I brought up earlier. Right, so we take the circumference and divide it by, which is in kilometers, right? As we determined that before. Circumference, the kilometers, and then we're going to divide it by the total hours covered by the 12 images, which we found in question 2. And this is in hours, right? Right? Well, with the distance divided by time, this is a velocity. Right? Well, this makes sense. We have, just like I said before, when you look at these 12 images, you're basically looking at the amount of time it takes for this X, which is a specific location in this red spot, right? To go one full rotation, to go around once, all right? And since we know the circumference, we know the distance that this takes, right? So we take the distance divided by the time it takes to cover that distance. That essentially gives a velocity, all right? So question 3, you're going to end up getting the velocity in kilometers per second. All right, now how about this last question? This last question 4 says our previous calculation is the approximate speed in 1979. What is the rotation period at this distance from the center of the Great Red Spot? Well, this is kind of a question that's asking the same thing as something we found already, right? So we know that one rotation period is shown in this group of 12 images, right? One rotation period of this x is shown here because we see that in image 1, the x is here, and image 12, it's at the same spot. It's gone around once. So question 4 is pretty much asking us the same thing as question 2, all right? But what you need to do is actually convert that, right? So in question 2, you found how many hours. I want you to convert that in number 4 to days, all right? So should be in days. Garbage handwriting, but it's okay. Question 4 should be in days because you found it previously in hours. So we have just found the velocity of this little point x around the pretty much outer edge of the Great Red Spot, right? And since this x is supposed to represent some point that we saw of the Great Red Spot, this is a good estimation of, this velocity is a good estimation of the wind speeds in the outer edge of the Great Red Spot. And so in part B, what you're doing is you're going to take that velocity that you found of the Great Red Spot, and you're going to compare it to some of the strongest cyclones that exist on Earth. And this particular one is talking about the one from April 22nd, 1991 in the Bay of Bengal, right? It says it reached 258 kilometers per hour. So you're going to, for question 1, you're going to quantitatively compare the maximum speed of the cyclone to your value for the Great Red Spot. How many times faster are the wind speeds on Jupiter? All right, so let's do a quick, I want to show you how I want you to do this, all right? So previously you found the velocity of the Great Red Spot, all right? And you also found, well, you're given the velocity of a cyclone, okay? Which, remember, is the 258 kilometers per hour for over here, all right? So what you're going to do is you're actually going to divide these numbers, all right? Now, so you're going to take the velocity of the Great Red Spot divided by the velocity of the cyclone, all right? And this is going to give you some number, all right? Now this number tells you how much larger the velocity of the Great Red Spot is than the velocity of the cyclone, all right? For example, let's just put numbers in there. Of course, they're not necessarily real. But let's say the velocity of the Great Red Spot was 400, right? Let's say it was 400 kilometers per second. And for, let's say, just for purposes of an example, let's say the velocity of the cyclone was 200 kilometers per second. All right, note this was the Great Red Spot. This is the cyclone. The answer to this, 400 divided by 200 is 2, right? This, and just like I said before, this is supposed to tell you how much larger the Great Red Spot's velocity is than the cyclones. This makes sense. 400 is twice 200, right? So it's twice as large, right? So that's what you're going to do for question 1 here. Question 2, let's clear the board first. Question 2 asks you to quantitatively compare your results to the range of values and comment. All right, so this is telling you what scientists has actually measured the Great Red Spot. And they've actually measured 610 kilometers per hour. Right? And so what you're going to do is you're actually going to find the percent difference between the value that you found and the value that they have. Right? And remember, just the percent difference is equal to the absolute value of the actual value minus your calculated value all over the actual value times 100. That gives you a percent. All right? So your actual value, these two things in question 2 are equal to 610 kilometers per hour, and your calculated value is that found from part A. All right. And question 3 is just asks you, what do you think are possible sources of error in our measurements? Well, what is the first thing we assumed here? The thing we assumed was that we knew what the circumference was, right? And to think back of how we found the circumference, we pretty much just estimated, right? We said it looked kind of like 1.25, so it kind of makes sense that since the velocity is directly dependent on the circumference, that if our circumference has introduced some type of error, right, whether that be from us just estimating it or anything really, then of course that's going to be pretty much the primary source for error is going to be how we calculated the circumference, right? And that should make sense to you. Okay, so now we're going to go on to part C, which has to do with the Galilean moons. Now, in the first kind of prompt here, it tells you to use a transparency. Well, obviously, that has to do with in-class students. So for you guys actually need to retrieve this. And it is not in the lab manual that you have from Blackboard. You actually need to go to my website and download the Word document from there. So go to my website, www.corysargentphysics.com, which some of you probably are watching this video from that website right now. Go to the For Students, go to physics courses. There's a bunch of physics courses here. Go to your astronomy class, so the first one on there. Go to lab material, and this has all your labs that I'm up to date with, right? And we're doing lab 8, so all you need to do is click on this lab 8 manual, and it'll automatically start downloading the Word document, right? And of course, the guide too is right next to it, so I highly recommend you do that too. All right, so the important part about what you find in the Word document from my website is at the very bottom, there's an extra page that has something that looks like this. And these are the images that part C is referring to. So I'm going to slide that over to the side and look at the questions. They're both of them have the same questions, but let's just look at them side to side here. So each one of these nights, right, each one of these rows is an image taken from Earth of Jupiter, all right? So you're looking at Jupiter and its moons from the side, right? So if we were looking at Jupiter from above our solar system, you'd see these moons going in a bunch of circles, right? But you're not looking from above. You're actually looking from all the way over here, for example. So you're looking at it from the side. So you're not going to see these nice circles. You're going to it's going to look like the moons are going side to side. And that's exactly what you're going to be measuring here. All right, and let's go to question 4 here. It says, for each moon, estimate the orbital period. Remember that the orbital period is the time it takes to complete a full orbit. Well, how do we know if a moon makes a full orbit if we only see it in straight lines? Well, if we can imagine looking at one of these orbits, if we can imagine looking at it from the side, that we know it makes one full orbit when it gets back to its original position, right? And so that's what we need to, that's the pattern we need to see over here. So once you download this, I recommend drawing on it. All right, you can go to the Draw tab or anything, or you can print it out and draw on it too. A nice, pretty blue picture. And we want to do this for every moon. And we're looking for, well, previously it says we want to make a dot for each one of these moons for each night. And then we want to connect all the dots. So I'm actually going to do one of these for you. We're actually going to work on the yellow moon, right? So I'm going to change this to yellow, right? So in night 1, we're here. Night 2, we're here. 3, 4, 5, 6, 7, 8, 9. So I just enlarged them a little bit. So we're going to connect the dots from here to here, here, all the way. So we can clearly see the side-to-side motion, right? And we see that it looks to move to the left, and then it stops and it goes back, and it comes back to its original position, right? Now what's going on here is that, for example, let's take this outer circle. For example, you're seeing it at this point, and then you're seeing it again at this point, right? So this corresponds to night 1. This corresponds to night 2. Night 3 that's all the way over here, right? As you can see, it's still orbiting around. It's not going in straight lines. It's just how we perceive it. It's going in straight lines, right? And then night 4, right? So this is night 1, 2, 3. Night 4, it's around this location. And then night 5, we're back to our original spot, right? So this is 5 nights. So how many days is that? Well, let's take, for example, between last night and tonight, how many days is that, right? That's 2 nights, but there's only been 1 day. So similar to our problem in part A with the images, we have a similar case here. So it takes 1, 2, 3, 4, 5 nights for it to go all the way back to its original position. But that's actually 4 whole days, right? That's a day, that's a day, that's a day, and that's a day. That's 4 full days. So the orbital period itself is 4 days. That's for the yellow moon. Right? So here, the yellow moon is going to be associated with, is 4 days, right? So I'm just going to type 4 days in the orbital period. Now your job is to find the orbital period of the rest of them using the same logic. Now question 5 goes a little bit further. Now it says, using the image on the previous page, figure out which colored dot is which moon. Now the previous page, this is actually supposed to be down there a little bit more. So the previous page is this page. This is the image it's referring to. So using the image on the previous page, figure out which colored dot is which moon. All right, so really what you have to do is look at all these moons. And we can see that the furthest extent that it gets to is around this point, right? So this is about the furthest it gets that way, and this is about the furthest it gets that way. And what does that mean? Well, that tells us pretty much that that is the orbital radius, right? Because if it doesn't extend that far out, that means that, let's go back to our little map here, that it would be at that location. Because we don't see it going this way anymore, right? It only goes back towards Jupiter, at least from our perspective, right? And then as it goes to the other side, it doesn't go this way anymore, right? It only looks to go back towards Jupiter in our perspective, right? And so what we're seeing is that when it's at this point, at these maximum points, right? When it's at these maximum points, the distance between them, at the points where it doesn't go to the right any further or to the left any further from this way, that's actually the orbital radius, right? Because let's go back to the other page here. Let's draw a giant eyeball, right? We see this distance, right? That's just the orbital radius, right? And what's special about this plot, this picture in particular, is that it tells us, let's zoom in a little bit. Right here, it tells us which moon, so either Callisto, Europa, Io, or Ganymede, which moons have the smallest orbital radius and which ones have the largest, and in between, of course, right? And so once we look, so for example, the blue moon, I'm back on the right-hand side. The blue moon looks to have an extent out to here. The red moon, looks to not go that far, right? So the red moon has an orbital radius that only extends that far. And the white moon is actually all the way out here. We see that it actually takes a while to go all the way. All the way. So we see that the red moon actually has the smallest orbital radius. Well, let's look at this image on the left-hand side. We see that the smallest orbital radius is this one, and that is little Io. Right? And of course, with that same logic, we can find which one of we can find pretty much all of them by using the same logic and applying them to each one. Right? So that gives you up to question 5. Now, question six asks you, following the blue dot, for example, it reaches around the the +1 and the -1 on the observations. Right, so, nope. I'm going to erase some of our stuff so we can get a nice clean spot. All right, so it's asking about the blue dot now, right? So it's telling us that the blue dot gets around this ±1, all right? And it's telling us that this distance from Jupiter to the number 1 is our scale here. That distance is actually 665,000 miles, all right? And so on night 1, we see that this blue moon is about this distance away from Jupiter. All right, and that is the extent that this moon goes, so that is actually its orbital radius. So for question 6, it's pretty easy because we know that it's just 665,000 miles. Now question 7 is a little bit tricky. It says, how many miles away is that same moon on night 3? Well, the wrong answer is to try and say that this is a fraction, some fraction, and that this is the distance you want. That is the incorrect answer, right? We've just stated that the blue moon at this location, represents the blue moon's orbital radius. And previously we've said that the orbital radius, that these moons are circular orbits. What does that mean for our orbital radius? That means our orbital radius is always constant, right? Because a circle is a circle. A circle has a constant radius. So how many miles away is that same moon from Jupiter on night 3? Well, it's always the same speed away. And in the previous one, you found the same speed. It's always the same distance away. So in question 6, you found that distance. So it's always that distance away. Every night, right? Because they're not going back and forth like they look like they are in these images. We know for a fact that they're moving in circles, right? So using this chart, again, we're going to do a quick rundown. Using this chart, you're going to count how many full days it takes for these moons to go back to their original positions. That's their orbital period. And then using this image and the logic of trying to find their orbital radii, you're going to determine which moon is which. Right? And then it asks you a question about the blue dot. The blue dot, of course, the blue moon. And the blue moon has an orbital radius of about 1 unit, which is 665,000 miles. And in question 7, we realize that they're circular orbits, so their distances do not change once we know their radius. Since we found the radius in question 6, we obviously know how many miles away it is on night 3, and night 4, and night 5, and so on. Okay, so now we're on the final part, the mass of Jupiter. Now the cool thing here is that we're actually going to use all the information that we found about one of the moons from part C. We're actually going to estimate the mass of Jupiter. Right? And the equation that you're looking at, the equation that you'll be interested in, is this one right here. All right? That is the equation you're going to be using. All right? So, and you're also given big G. Right? That's big G. And you're looking for the mass of Jupiter, M. Now, what do you plug in for P and A? Well, for P, you're going to be using, so let's pick one moon. So let's say whatever values you got for Io, right? You can use any one of them, whichever one you think is easier. But we need, from part C, we need the orbital radius, and we need the orbital period. All right, and so let's see, I'm going to take a look at the lab guide, right? This is available to you from my website too. All right, we need the orbital radius in meters and the orbital period in seconds, right? And this is so we can get a mass in kilograms, right? So we have, from part C, for one of the moons, we have an orbital radius in miles, we need it in meters, and we have an orbital period in days, and we need that in seconds. Right, so I'm going to write that. Okay, so those are values that you should be able to convert on your own, all right? So now let's look at this equation here. All right, so we have p squared equals 4 pi squared over gm times a cube. Now note that even though we have this a cubed like that, multiplied by this fraction, that's the same thing as multiplying it by 4 pi squared over gm times a cubed over 1, which is just 4 pi squared a cubed over gm. Same thing, just different ways you can write it. We want to solve this for m, right? So let's go ahead and erase this just so we don't confuse ourselves any more than we have to. Let's multiply both sides by m. We want m by itself and in the numerator. So we're going to multiply both sides by m. Right? This leads to us canceling these m's. And we get m times p squared on the left-hand side times 4 pi squared a cubed over big G. Well, now like I said, we want m by itself. So let's divide both sides of the equations by p squared. All right, which is the same as multiplying by 1 over p squared, right? So on the left-hand side, these p's cancel. And we are left with m by itself, just like we wanted, is equal to 4 pi squared a cubed over p squared g. Now this is the equation that we're going to want to plug things in, because we are looking for mass, right? And if you put a, if you converted that correctly into meters, and p correctly into seconds, then your mass will be in kilograms. That's why these conversions are really important. Okay, you can look at previous labs if you need a refresher of how to do conversions like that. We've done it plenty of times. All right, so in this case, we're going to find a really large mass for Jupiter. And it actually should be pretty close. You should definitely get the same magnitude, All right, you should get something times 10 to the 27th. All right, so you should be on the same magnitude, which magnitude just is this number I'm referring to, right? So for question 2, the last problem on this lab is that you're going to find the percent difference between your calculated value and Jupiter's actual mass. All right, and this is the second time in this lab that we're doing a percent difference, but we'll write it down again. Remember, is that equal to the absolute value of the actual value minus the calculated value over the actual times 100. Right? Let's see. Make sure we can see that. Right, your actual value is given to you. It's the 1.898 times 10 to the 27th. That's this value right here. Your calculated value is what you found here. All right, and as a hint, if you get question 1 correct, your percent difference should be anywhere between less than 100%, right? You should be pretty close. It's not going to be less than 10 unless you got a really good number, but it definitely should be less than 100, 110% as your percent difference. All right, so hopefully this little video helped a little bit. I know it's not the same as being in person, but don't forget that you also have a lab guide available, right? So now you have this video available, and you have this lab guide that's written. In this lab guide, I pretty much talk about the same exact stuff, but just written down. So, and I do go over part C, in case that could be a little rough. So I go over part C, I do the yellow moon, and then I talk a little bit more about part D. Okay? So, hopefully this helped, and I will see you all next lab.